Welcome back to a new session of the MOOC on Information Security. Here we will see symmetric key and public key signature. In the previous session, we learned that a digital signature is a mathematical technique used to validate the authenticity and integrity of a message, software or digital document. It's a way of encrypting our message to communicate securely over a network. Hope you are now clear about the symmetric key cryptography and asymmetric key cryptography techniques. The first one uses any cryptographic algorithm that is based on a shared key which is used to encrypt or decrypt text or ciphertext, in contrast to asymmetric key cryptography where the encryption and decryption keys are different. Symmetric encryption is generally more efficient than asymmetric encryption and therefore preferred when large amounts of data need to be exchanged. Establishing the shared key is difficult using only symmetric encryption algorithms. So, in many cases, asymmetric encryption is used to establish the shared key between two parties. Examples of symmetric key cryptography include AES, DES and triple DES. Key exchange protocols used to establish a shared encryption key include Diffie-Hellman, elliptic curve and RSA. We already covered all these topics. Digital signature standard. The National Institute of Standards and Technology or NIST has published Federal Information Processing Standard FIPS 186 known as the Digital Signature Standard or DSS. The DSS makes use of the secure hash algorithm or SHA described in one of the modules and a new digital signature technique. The digital signature algorithm or DSA. The DSS was originally proposed in 1991 and revised in 1993 in response to public feedback concerning the security of the scheme. There was a further minor revision in 1996 and in 2000 an expanded version of the standard was issued as FIPS 186-2, subsequently updated to FIPS 186-3 in 2009. The DSS uses an algorithm that is designed to provide only the digital signature function. Unlike RSA, it cannot be used for encryption or key exchange. Nevertheless, it is a public key technique. Figure 1 contrasts the DSS approach for generating digital signatures to that used with RSA. In the RSA approach, the message to be signed is input to a hash function that produces a secure hash code of fixed length. This hash code is then encrypted using the sender's private key to form the signature. Both the message and the signature are then transmitted. The recipient takes the message and produces a hash code. The recipient also decrypts the signature using the sender's public key. If the calculated hash code matches the decrypted signature, the signature is accepted as valid. Because only the sender knows the private key, only the sender could have produced a valid signature. Approaches for digital signature. Public and private keys can also be used to create a digital signature. A digital signature assures that the person sending the message is who they claim to be. Typically, we use the recipient's public key to encrypt the data and the recipient then uses their private key to decrypt the data. However, using the scheme of digital signatures, there is no way to authenticate the source of the message. A reason for the growing popularity of encryption is increased use of emails. Emails are handled with email protocols such as simple mail transfer protocol. But it is desirable that the mail handling protocol should not access the plain text form of the message and the recipient wants some assurance that the message is from the assumed sender. Hence, the two commonly used approaches for digital signature to provide authenticity and integrity are symmetric encryption approach and public key encryption approach. Symmetric encryption approach. In symmetric encryption, data is encrypted using a key and the decryption is also done using the same key. Using symmetric key encryption, the decentralized key distribution scenario is impractical. This scheme requires the sender to issue a request to the proposed recipient, wait for the response, which includes the session key, and then send the message. A key distribution sender, or KDC, in cryptography is a system that is responsible for providing keys to the users in a network that shares sensitive or private data. Each time a connection is established between two computers in a network, they both request the KDC to generate a unique password which can be used by the end system users for verification. With some improvements, the key distribution sender, or KDC strategy is an aspirant for email. Because we wish to avoid requiring that the recipient and sender need not be online at the same time. Public key encryption approaches. Public key cryptography involves a pair of keys known as a public key and a private key, or a public-private key pair, which are associated with an entity that needs to authenticate its identity electronically or to sign or encrypt data. Each public key is published and the corresponding private key is kept secret. Remember that for this strategy to work, either the sender know the recipient's public key or the recipient know the sender's public key, or both. Encryption with secret key for single time is enough for confidentiality. But if authentication is of primary concern, then a digital signature may do. This method guarantees that later the sender can't deny having sent his message. But there is a possibility for another fraud. Let's again use the example of Alice and Bob. Here, Bob composes a message to his boss Alice that contains an idea to make profit for their company. He appends his digital signature and sends it as email. Eventually, the mail is get delivered to Alice's inbox. But suppose that Mike has heard of Bob's idea and gains access to the mail queue before delivery. He finds Bob's message, strips off his signature and appends his, and then requeues the message to be delivered to Alice. What happens? Mike gets credit for Bob's idea. You can connect a number of similar scenarios in your life, right? To counter such scheme, both the message and signature can be encrypted with the recipient's public key. An effective way for this is the digital certificate. In addition to the message, A sends B the signature encrypted with A's private key and A's certificate encrypted with the private key of the authentication server. The recipient of the message first uses the certificate to obtain the sender's public key and verify that it is authentic, and then uses the public key to verify the message itself. If confidentiality is required, then the entire message can be encrypted with a one-time secret key is also transmitted, encrypted with B's public key. The model of a digital signature scheme based on public key cryptography is depicted in the following illustration. Each person adopting this scheme has a public-private key pair. Generally, the key pairs used for encryption or decryption and signing or verifying are different. The private key used for signing is referred to as the signature key and the public key as the verification key. Signer feeds data to the hash function and generates hash of the data. Hash value and signature key are then fed to the signature algorithm, which produces the digital signature on given hash. Signature is appended to the data and then both are sent to the verifier. Verifier feeds the digital signature and the verification key into the verification algorithm. The verification algorithm gives some value as output. Verifier also runs same hash function on received data to generate hash value. For verification, this hash value and output of verification algorithm are compared. Based on the comparison result, verifier decides whether the digital signature is valid. Since digital signature is created by private key of the signer and no one else can have this key, the signer cannot repudiate signing the data in future. Algorithms. There are three algorithms associated with digital signature. They are key generation algorithms. Digital signature is a method to assure that the message was sent by a particular sender. While performing digital transactions, authenticity and integrity should be assured, else the data may be altered in transit or someone else can act as the sender. The second one is signing algorithms. To create a digital signature, signing algorithms create a one-way hash of the electronic data which is to be signed. The signing algorithm then encrypts the hash value using the private key called the signature key. This encrypted hash along with other information like the hashing algorithm is the digital signature. This digital signature is appended with the data and sent to the verifier. Using hash instead of the entire message saves time, as now instead of signing a long message, a shorter hash value has to be signed, and moreover, hashing is much faster than signing. The third algorithm is signature verification algorithm. Verifier receives digital signature along with the data. It then uses verification algorithm to process on the digital signature and the public key and generates some value. It also applies the same hash function on the received data and generates a hash value. Then the hash value and the output of the verification algorithm are compared. If both of them are equal, then the digital signature is valid, otherwise it is invalid. A detailed study of the digital signature is done in this module. The different strategies such as symmetric and asymmetric or public scheme of creating digital signatures and the features of both the schemes are examined. We just had a description of different algorithms required for the processing of digital signature. Hope you understand the session. See you next time. Bye.